So we've been talking about chain rule. And so this is the last example we were looking at. So in this example, we're given, three functions. So I have y is a function of u is a function of w, and w is a function of x. So we want to find dy dx. So what's helpful is to draw the old, what I call variable chain. So y is a function of u is a function of w, and then finally here we have w is a function of x. So chain rule says, so starting with dy dx, that's what I want to find. If we look, the only function of x is w. So this last derivative here is going to have to be dw dx. Because the way chain rule works is we want the dx as the very last variable here. So whatever's down here should show up as the very last variable at the bottom here. And so now I need to fill in, I need a bridge. So I need a bridge right here. So I need something that'll connect w. So now we need to connect w and y. So according to chain rule, the most natural thing to write down is dy dw. This becomes our link. Here's my bridge between the two derivatives. And so that's what I have written here in my first line. I first do dw dx here, and then the bridge between w and y, which is dy dw. And the way the notation is set up is you can sort of think how we're kind of canceling those. You have your dy dx. But now there's one small issue. If we look at y, it's not a function of w. So now I need to calculate dy dw. And I'm playing the same game now. If you look, the only function that's a function of w is the function u right here. So this last derivative is going to have to be du dw. Because I want this w. And now I need a bridge between u and y. So the most natural thing to write down according to chain rule is dy du. Which makes sense. Y is a function of u. So basically now I can replace the dy dw with the dy du dw. And so that's what I have here. I calculate dy dw, and then I plug it in for this term gets replaced with this term. And so that's our final answer there. So this problem is kind of annoying. You wouldn't see something like this on a test. This is maybe a homework problem, but it's just for us to get used to variables and thinking more abstractly, to see the structure of things, how things are related, and how to work within that structure. So I have one last chain rule example, and then we'll move on to more chain rule. So here we're given that y is a function of x. We don't know what the function is. We just know y is a function of x. And we're told x is itself a function. So we don't usually do this. This is a little weird. So we're told x is a function of the variable r and the variable theta. And r and theta are independent variables. So they're not related to each other. R and theta are two separate, if you want to think of separate axes, you can. They're not related at all. So if I make the variable chain, I have my function y. It's a function of x. But now look at this. X is a function of two variables, r and theta. So in an indirect way, you can see that y depends on r in an indirect way. And you can also see in an indirect way, y depends on theta. So if we go down this way and this way. So now to find the derivatives, we're going to just use chain rule. So we want dy dr and dy d theta. Those are reasonable derivatives to ask for. For the first one, dy dr, I'm going to treat x just as a function of the variable r. So here I say x equals g of r. So that's me saying I'm going to treat x as a function of the variable r only. And the function looks like r times cosine theta, where the theta I'm treating now as a constant. Because here I'm thinking of x now as only a function of r. R is the only variable. So according to chain rule, if I want to find dy dr, so I do dy dr. So on the other side, you start with the numerator, dy, and just follow the variable change. So if I look at y, the only variable I can take the derivative of y with respect to is dx. So just do dx, dy dx, and now look at x. This term down here tells us to now look at the x derivative. And so now if I look at x, I now want to do dx dr. And that'll give me the derivative. So here you can see we're not canceling, but in a roundabout way, you can see the dx in the denominator here and the dx up here, they counteract each other. So now that's the formula. I just now have to calculate dy dx and dx dr. So that's what I've written here. I've written dy dr equals df dx. So why do I say df dx? Well, f and y are the same. F and y are the same. So remember here, dy dx would be the same as df dx. Okay, I'm just changing the notation a little bit here because I want you to practice a little bit seeing the strange notation, okay? So this df dx is the same as dy dx times dx dr. Again, remember x and g are the same. So here, this is dy dx, dg dr. The derivative of y with respect to x is just f prime because we don't know the function here. We're not given the function. So here, the derivative of y with respect to x is just f prime. The derivative of g with respect to r, so I'm taking the derivative of r cosine theta with respect to r, and I'm treating theta like a constant. So here, this is just like a constant times r, and the derivative of r with respect to r is just like the derivative of x with respect to x. It's just 1 by the power rule, if you wish. So the derivative of r cosine theta would be 1 times cosine theta or just cosine theta. So there's dy dr. And in the same way for dy d theta, I assume x is a function of theta only. That is here, I'm treating r now for this part as a constant. Theta is the only variable. And again, we can use chain rule. Chain rule says dy d theta is going to be dy dx. So remember here that f and y are the same. So here, instead of f, I could have written y here. Let me do that. So here, this would be dy dx times, and then for the denominator, it tells us to look at the derivative of x. And so here, I'd have dx d theta, dx d theta. And now we calculate. So dy dx, as we said, is just f prime, dy dx. Dx d theta, we're taking the derivative of r cosine theta with respect to theta. The derivative of cosine theta is minus sine theta. So the derivative of r cosine theta is minus r sine theta. And so that's what we see here. We've got the f prime of x, and then you see this minus sign is from the derivative of the cosine, minus r sine theta. That's the derivative of r cosine theta. So that's what the derivative looks like, and I put the variable chain here. So yeah, this is a little trickier than what we would see in Calc 1. Full honesty, don't be mad at me, this is actually a Calc 3 problem. but y'all are stout, you're strong. I know you don't get intimidated, so I just did this problem. Of course, you'll never see this on a test in Calc 1, but since we're here, I thought I might as well do it. And I'll talk about R and theta later. Okay, so R and theta are famous variables and will come up in a big way in Calc 2 and Calc 3, and we'll talk about them a little bit later. So that's chain rule in all its glory. And now that we've done chain rule, the best thing to do is some more chain rule. So, but instead of calling it chain rule this time, we're going to call it implicit differentiation because it sounds more complicated, makes it seem a little harder. So call it implicit differentiation. But please, people, the most important thing I can tell you is implicit differentiation is the same as chain rule. Okay. So I want to motivate implicit differentiation. There's a particular scenario in when we're using implicit differentiation. That's why I want to motivate the scene. Okay. So the situation is we have y is a function of x, but the problem is we don't know the formula. So I know y depends on x, but the formula for f of x is unknown. What I do know about y, though, is that I do know y satisfies an equation. So in this example, I just made up an equation. So here, even though I don't know what y is as a function explicitly, I do know that it satisfies an equation. So in this particular case, I know whatever y is, it satisfies the equation y cubed plus xy equal to x. Just an equation I made up for this example here. So the question now is, if we don't know what y is, but we do know that y satisfies some equation, can we find the derivative dy dx? So obviously the answer is yes. Otherwise, I wouldn't be talking about it. So the answer is yes. And what's the concept though? So one straightforward thing to try, and this is, a very natural thing to try, is to try and solve the original equation for y. When I say explicitly for y, what I'm trying to do is I'm trying to get an equation where I have y by itself and equals and everything else on the other side. That's what I mean by solve explicitly for y. That's when you get y by itself on one side of the equation. However, in this case, it's not easy, maybe not even possible. Okay, so trying to solve for y first, even though that seems like a very reasonable idea, may not be a practical idea, may not be easy to do. But it turns out we actually don't need to do that if we're looking for the derivative. We can just take the derivative first, don't even solve for y, take the derivative first, and then solve for y. So these two steps is what's known as implicit differentiation, where you take the derivative of both sides of some given equation first, and then solve for y prime. These two steps here are what's known as implicit differentiation. And so let me do that here. Let me now show you how that works in this particular case where we're given this equation. Okay, so what I'm going to do now is I'm going to calculate implicitly the derivative of y cubed, and I'll explain the theory behind that. And then I'm going to find the derivative, again, using implicit differentiation of x times y. And then I'm going to find the derivative of x, that we can just do. And then we'll solve for y prime and find the derivative. So let me show you how this procedure works. Let me start with y cubed. So the most important thing when doing implicit differentiation is to remember that, for example, here we're assuming y is a function of x. So when we're talking about an expression that looks like y cubed actually looks like f of x cubed. And now you should be thinking chain rule. F of x cubed is a composition of functions. The inside function is f of x. The outside function is the cubing function. So now let's take the derivative of both sides with respect to x. And I want to now just focus on this form here, d dx of quantity f of x cubed. As you know, this is a composition. So I'm going to do a chain rule. I need to bring the 3 down times f of x raised to the 3 minus 1. So when I do that, the derivative of the outside looks like 3 times f of x squared. That's just the derivative of the outside. I now need to, we're peeling the onion, so we've gotten rid of the cube part. I now need to do times the derivative of the inside function, which is just f of x. So here, since we don't know what f of x is, the derivative of f of x we write down just as f prime. So the derivative of f of x cubed is 3f of x squared, derivative of the outside, times f prime of x, which is derivative of the inside. So let us now write this in terms of y. In terms of the variable y, the derivative of y cubed looks like 3y squared, so here this f of x got replaced with a y, times y prime, this f prime got replaced with a y. So I want you to now kind of focus on this equation here. The derivative of y cubed equals 3y squared y prime. And that's basically, a great example of implicit differentiation here, where we don't know what y is, but we're able to find the derivative. And what you should see, for me, it's really helpful to think of y cubed, as I said, to think of it in this form, that you can replace the y, in your mind at least, with f of x and think of this as a function of x cubed. And that's a composition, so I need chain rule. So here, both of these formulas are good, and you should take a look at both of these and make sure they make sense to you. In blue, that's the implicit differentiation on when it's f of x cubed, and in red, that's implicit differentiation when it's in the form y cubed. So what we'll see usually is we'll have the equations in the form where the function of x is just given as y, not necessarily anything else. So to finish the derivative, so here I've only taken the derivative of the first term, y cubed. I want to also show you for xy, we have to be careful. So for the derivative of x times y, we're going to use a product rule. It's important to realize that when we say x times y, what we're really saying is x times a function of x times f of x. And there I see a product of functions of x, therefore I need to use product rule. And so now we're going to do, derivative of the first function times f of x. So there you have derivative of x is just 1 times the second function is f of x. And then you know how product rule goes. Then we do plus, so there's my plus symbol right here. Copy down the first function times the derivative of f of x. Derivative of f of x is just f prime. And finally, if we go back to the variable y, here's the formula that I really basically want you to focus on, is that the derivative of x times y is y plus xy prime. And that should make sense to you as a product rule. That when I see x times y, I think, oh, that's x times a function of x. So I'm using product rule. Then I do derivative of the first times the second, plus the first function, which is x, times the derivative of y with respect to x is just y prime or dy dx. So here you can write either y prime for the derivative of y with respect to x. So here y prime is the same as dy dx. You could write either. It's good to be able to do it both ways. You know what I mean? So here y prime or dy dx. So okay, let me now do this problem completely. So the question now is, suppose we know y is a function of x, and suppose we know y satisfies this equation. We want to find the derivative dy dx. So we're going to start by differentiating both sides of the equation with respect to x, the left and right side, and then solve for y prime. So let me show you how that goes. So here I have I'm indicating I'm taking a derivative of both sides. For the left side, the derivative of the sum is the sum of the derivatives, so I break that up. And now you saw for the derivative of y cubed, the derivative of the outside is 3y squared times the derivative of the inside for my chain rule is y prime. And then for xy, here we're using a product rule. And the derivative of the first times the second, and plus, the first times the derivative of the second. So there's the product rule. And here, when we're doing x times derivative of y is just y prime. And then on the other side, we get one easy derivative here. The derivative of just x is, with respect to x, is just 1, right? So the derivative of x is just 1. So yeah, now it's just algebra. We've done the calculus part. Now I want to group the terms that are being multiplied to the y prime. So 3y squared times y prime and xy prime, I want to group those and factor out the y prime. And this y here, I'm going to put on the other side. So I'm going to end up with 3y squared plus x, quantity y equals 1 minus y. So final step, I want to isolate the y prime. So I'm going to divide both sides by 3y squared plus x. And so my final answer for the derivative is dy dx, or y prime, equals 1 minus y divided by 3y squared plus x. So this is implicit differentiation. And the things to notice is, one, we know y is a function of x, but we don't know f of x. Two, we know y satisfies some given equation. In this, and three, we want to find dy dx. So in this scenario, this is exactly when we use implicit differentiation. You have to resist the urge to try and solve for y first and then take the derivative. Here you want to take the derivative and solve for y prime. And so here, if you look at the final answer, our derivative has the variable y in it. So we still, at the end of the day, don't know what the function y is, but we've found its derivative in terms of itself, which is unknown, which is fine. This is how implicit differentiation works. So that's the theory of implicit differentiation. Typically the algebra is the hardest part. Once the derivatives people are okay with. So let me give you just a little more theory, and then we'll just do a bunch of examples. So the idea starts with the concept of an implicitly defined function. And I want you to contrast the word implicitly with the word explicitly. So what's an explicitly defined function? Would be a function where y is by itself already on one side. So here, this would be an explicit. And when we're given a definition of a function where it's not explicit, where you don't have the y, just by itself on one side, then that's called implicit. Okay, so let me give you an example here. So up until this point in this class, and maybe even in pre-calculus, we've been very spoiled in the sense that we're always just given explicit functions, right? We're always told y equals something and then find dy dx or whatever, or find the limit or whatever. Now, we don't have this nice explicit form necessarily. Now, we're stuck in the situation where things are defined implicitly. Okay, so let me show you an example. So here's the theory. Suppose we have any equation of the form f of xy equal to k. Okay, so let's be very careful. What this is saying, and when they say f of xy, that means on the left-hand side, we have an expression that involves the variables x and y. So here I'm just making up something, xy times root y. I just made it. So this would be capital F of xy equal to, and on the other side, k is some constant. So I'm just randomly pick the number 3. So given an equation like this, you see it's not explicit for y, okay? We claim this equation can be used to define a function. We can use this equation to define y as a function of x. How so? In theory, for each x, if you give me an x value, so for example, suppose I now say let x be 6. In theory, if you give me an x value, suppose x is 6, so then in theory, I can solve this equation, 6y plus root y equal to 3. I can solve this equation for y. So given this equation, that's this implicit equation, you give me a constant, an input value x, I can plug in that input value, then I get something that's only has one variable in it. It's the only unknown once you plug in for x is the variable y. And then in theory, at least, we can solve that equation for y. So here's your input-output machine. You give me an X value, I plug it into the equation, I solve the equation for Y, I spit out the output. So that's an implicitly defined function. The idea is that we don't have Y equals, we have some equation that X and Y satisfies. And we can use that to, in theory, find values of Y. Let me do an example here. Once you see an example, it gets a little better. So let me use the previous equation we had. So starting with this equation, I'm going to use this to define Y as a function of X. So first thing I'm going to do is I'm going to move the X over to the left side. I'm going to move this X over because what I want is I want all the X and Y variables on one side. I want to make it look like this equation here, f of xy equal to k. What that means is all the X and Y variables are on one side. So when I move the X over, then if you look, we exactly have an equation of the form f of xy equal, so there's my equal symbol, to k. And you can see on the other side here, k is trivially 0. Doesn't always have to be, in this case it is. And so here's my equation, f of xy equal to 0. This is, an example of this f of xy equal to k type implicit form. And in theory now, we can use this equation to define y as a function of x. So how does that work? If you give me an x value, so you say, suppose x is equal to 1, then I would replace this x right here with the number 1. And in theory now, we can solve this equation. The only unknown is y. So now the equation looks like y cubed plus y minus 1 equals 0. In fact, we can solve this equation for 3 values of y in theory. And we choose one of those to be our output. So for any x value, we can find an output. We can find a y value using this equation. So this equation defines a function implicitly. Okay, so it's good to contrast this with an explicitly defined function. If I had a function just like this, y equal to x squared plus x, that's explicitly defined. I know exactly how to get y values from x's. There's no solving for y. I just plug in and then it spits out the y. This would be explicit, as opposed to the implicit where you're going to have to solve the equation for y. But anyway, we never actually solve anything for y because it's just in theory. What we're interested in are the derivatives. So this concept is related to a larger theorem called the implicit function theorem that'll come up in Calc 3. So Calc 3 is also known as multivariate calculus. So remember in Calc 1, we only have x and y. And so Calc 1 is known as univariate. There's only one independent variable. In Calc 3, you'll have x, y, and z. And so here we have 2 independent variables. In Calc 3, x and y are both independent. In Calc 1, just x is independent. Okay, so when you do Calc 3 in multivariate calculus, you'll come across this implicit function theorem again. This isn't the first time you'll see this. Actually, it comes up in Calc 2 also. So yeah, I'll let you wait for that. So here's finally the procedure, and let me start doing some examples. At the end of the day, this is what we need to know, how to do the derivative. Again, implicit differentiation is just another derivative problem. If you want to categorize things, limit problem, derivative problem, integral problem. So, okay, here's the setup. Typically, we'll be given an equation involving x and y. We'll assume y is a differentiable function of x. To find the derivative using implicit differentiation, first, we have to differentiate both sides of the equation. And I want to emphasize the both sides of the equation part. Then we're going to collect all of the terms that are multiplied to y prime on one side, and all of the terms that don't have y prime in them, move them to the other side, because we're trying to isolate y prime. Then we're going to factor out the y prime and divide and isolate dy dx. So we did this procedure before. Let me do another example. So here we're given f of xy. So f of xy defines a surface, okay, not a curve, but like a surface. Can I draw a surface? Hold on. So like a surface in 3D, like This is kind of supposed to be like a carpet, 3D surface. So yeah, f of xy defines a surface in 3D. So here your axis, your axis on the bottom here are x and y, and your axis on top here is z. And you don't need to know any of this, but that's what's happening. And so we're told y is a function of x and it satisfies this equation. And of course, find the derivative. So this is, classic setup for implicit differentiation, because we don't know what y is, but we do know, we're given in the problem that y satisfies this equation, x cubed minus xy plus y cubed equals 1. So resist the temptation to solve for y. Instead, just take the derivative of both sides directly. So let's do this term by term. For the derivative of x cubed with respect to x, that's just going to be 3x squared. For the derivative of xy, remember y is a function of x. So for the derivative of x times y, that's a product, I'm going to have to use a product rule. And for y cubed, remember y is a function of x. So y cubed is f of x cubed. I'm going to need a chain rule. Okay. And on the other side, we just have the constant 1. So that'll be, an easy derivative there. So here's the derivative. As I said, for x cubed, the derivative of x cubed is 3x squared, just using power rule. And then the derivative of x times y using product rule is right here. Here's the derivative of x times y using product rule. The first function here is x, the second function is y. Derivative of the first times the second is 1 times y plus, copy down the first function is x, times the derivative of y with respect to x is dy dx or y prime. And finally here, you can see the derivative of y cubed. I need to use a chain rule. So the derivative of the outside is 3y squared times the derivative of the inside is 3y prime. And then, of course, the easy one on the other side, the derivative of 1 is constant, is just 0, right? Yeah, so that's the implicit differentiation. That's the calculus part. This is the part students usually don't have an issue with. Now we got to do the algebra and solve for y prime. So all the terms that have y prime connected to them, I'm going to keep on one side, okay? And don't forget here, I have to distribute. There's a minus sign here. I need to distribute the minus there and distribute the minus there. The other terms that do not contain y prime, the 3x squared minus y, I'm going to move all of these terms to the other side. So after distributing the minus sign and moving all the terms, I get minus xy prime plus 3y squared y prime equals the negative y becomes positive, the 3x squared becomes negative. So equals y minus 3x squared. And then I factored out the common term, which was the y prime. Last step, divide both sides by 3y squared minus x to isolate dy dx. So here's the derivative. I still have no idea what the function is. No idea, don't care. But we have the derivative of the function. So as a technique, this is very important that you realize what we're doing here, how to do it, and being able to realize that, oh, this is a product rule for the derivative of x times y, and for the derivative of y cubed, that's a chain rule. That part's really important. And like I said, for me, it always helps me to think about this as being, oh, well, y cubed is actually f of x cubed. And so, yeah, that's a composition. That makes perfect sense. I should do derivative of the outside times the inside, So I like to, when I start to get a little bit confused, try and go back to those types of basics. So, of course, now you'll see in the section, they'll rehash all the standard derivative problems that you love. So tangent line problem is the most basic derivative problem that we all need to be able to do. So, yeah, we can do tangent line problem here. So it says, find the equation of the tangent line to the function y equal to f of x at the point -1, 0. They don't tell us the function f of x, but they do tell us that f of x satisfies this equation. 6x squared plus 3xy plus 2y squared plus 17y equal to 6. okay? So what I want to remind you of is, first of all, the equation of the tangent line. As you know, the equation of the tangent line is y equals f of a plus f prime of a times x minus a. In this case, the a is -1. So you get y equals f of -1 plus f prime of -1 times x minus -1 is x plus 1, okay? And so the other thing we know, we're given, when they tell us that y equal to f of x, to find the tangent line at the point -1, 0, -1, 0 is a point on the curve. So if -1 is the input, 0 is the output. What I'm trying to say is that f of -1 is given to us here as 0, because the output for -1 is 0, so f of -1 by definition is 0. So we know f of -1, the x plus 1 part, that's fine. The only thing we don't know, and the part we need to now figure out, is f prime of -1. Now, here's something I think is very important to not get confused, is to remember that f prime of -1 is just the same. This equals y prime, where we plug in x equal to -1. So when I say I'm trying to find f prime of -1, what I'm going to find is y prime using implicit differentiation and then plug in a -1 for the x. Okay, so here's the implicit differentiation now. I start with the equation. I take the derivative of both sides. 6x squared, the derivative is just 12x. For 3xy, we need a product rule. 3x, I'm treating as the first function, y is the second function. Derivative of the first times the second is 3 times y, plus, copy down the first function is 3x, times the derivative of y is dy dx or y prime. For 2y squared, remember, y is a function of x, so I need a chain rule. The derivative of y squared here is going to be, so just the derivative of y squared is going to be, the derivative of the outside is 2y times the derivative of inside. The inside function is y, and the derivative of y is just y prime, or dy dx. And then don't forget, I've got a 2 already hanging around out front. So the derivative of 2y squared is just 4y prime. So, and then for 17y, the derivative is just 17 times the derivative of y with respect to x. The derivative of y with respect to x is dy dx or y prime. And of course, the derivative of 6, we get a freebie there. The derivative of 6 is just 0. Yeah, so this first line is all the calculus. The rest of it now is just algebra. I'm going to keep these 3 terms together because they all have y primes in them. These 2 terms, the 12x plus 3y, since they don't have y prime, I'm going to move it to the other side. And so when I do that, I have my 3 terms and I factor out the y prime. So 3x plus 4y plus 17 quantity all multiplied by y prime equals, when I moved the other 2 terms over, they became negative. So equals negative 12x minus 3y. Last step here to isolate the y prime. So I have y prime equals 12x plus 3y, negative 12x plus 3y over 3x plus 4y plus 17. So I factored out this minus sign. I factored out all the way in the front right here, okay? And I just want to emphasize, when we say y, remember y is actually a function of x. So we really mean 3 times f of x here. And we really mean here, when you say 4 times y, we really mean 4 times f of x. And now I'm going to replace all of these x's with a -1, because I want to calculate y prime at -1. So here, f prime of -1 is just y prime with the x's replaced by -1. And so I take the derivative that we found, this derivative from the implicit differentiation, and replace all of the x's with a -1. -1 here, -1 here. Here I have f of -1, f of -1. And of course, we know we're given f of -1 is 0. So f of -1 is 0. So I can plug in the zeros. I can do the math. I get 12 over 14 or 6/7. Don't forget what we've discovered. So 6/7 is the value of the slope here for our equation of the tangent line. So we now know everything. We can just assemble the tangent line. So it's f of -1 plus f prime of -1 times x plus 1. F of -1 is 0. F prime of -1 is 6/7. And then, you know, I just dropped the 0 and simplified it a little bit. Not really, I just dropped the 0. So here it's a standard tangent line problem. The part you should really focus on is this implicit differentiation portion, where we take the equation that we know y satisfies, we differentiate both sides, treating y like a function of x. That part's really important. You know, and we use chain rule for terms such as y squared or x times y, we use product rule. And then algebraically solve for y prime after taking a derivative. So that procedure is super important and is the point of what we're talking about here today. A lot of times, you know, in science, we're not given y explicitly. A lot of times in actual practical science, we have an equation that we know stuff satisfies, but we don't necessarily have a formula for everything in that equation. So this, you know, this technique is incredibly important. Anytime we can find things in an indirect fashion, that's why we're studying math. We're able to use these types of shortcuts. So here, I want to do an example involving some trig functions because, you know, that's part of what we're learning in terms of the derivatives and stuff. So here, suppose y is a function of x, and we have this implicitly defined function, you know, and y satisfies x times sine of 2y equals y times cosine of 2x. So the first and most important thing I would warn you, you know, of course, they say find dy dx. The number one thing I would warn you is do not try to solve this equation for y. It's not going to work out. What you should do is, you know, don't fall for that temptation. Instead, take the derivative of both sides immediately. And now, of course, be careful. Here, x times sine of 2y, that's a product. So I have to use a product rule there. Y times cosine of 2x. Y is a function of x. Cosine of 2x is a function of x. This is a product of functions of x. I'm going to, again, need a product rule. Okay, so here I'm going to start. So let me do the product rule of the equation on the left side. So remember how that works? I do the first function here is x. So I did derivative of x is just 1 times the second function. So that's where the sine 2y comes from. Derivative of the first times the second. And then plus, I copy down the first function, which is an x. Now, watch the derivative here. So here I want you to make sure this makes sense to you. The derivative of sine of 2y, that's a chain rule because y is a function of x. That's like the sine of 2 times f of x. So I'm going to do the derivative of the outside. The outside function is sine. So the derivative of the outside gives me cosine. And then you copy the 2y. Times the derivative of the inside function. The inside function is 2y. The derivative of 2y is just 2y prime. So this is the product rule of the left-hand side. So you should, you know, take a look at that, make sure that makes sense to you, and think about where the y prime came from. And now for the right-hand side, again, product rule. Derivative of y with respect to x will be y prime times cosine 2x plus y times the derivative of cosine 2x will be negative sine 2x times 2. There's the y prime, derivative of the first function, times the second. And then I copy down the first function. The derivative of cosine 2y is a chain rule, is negative sine 2x. So that's where this minus sign is coming from here. This minus sine 2x times 2, that's the derivative of cosine 2x. That's the calculus part. Now I put the terms that have the y prime together. So this term here has a y prime, and this term here has a y prime. So y prime cosine 2x, I moved over to the other side. It becomes negative. This sine of 2y, I'm moving to the right-hand side because it doesn't contain a y prime. And then I factor out the y prime and divide, and I'm able to solve for y, for the derivative. Again, we have no idea what the actual function is, but we're able to find the derivative. Let me do this one last example here. We've got 5 minutes, and then I'll stop. How are we doing on this product rule? I hope this one, okay. It takes a little time, and you know, our eyeballs have to get used to things. So it takes a little time. So that's that product rule. And then on the other side, for this function, we have the product rule right here. It's definitely a good review. You know, if you can go through these slowly, this is definitely a good review with all the theory and everything like that. So yeah, the next problem is an implicit differentiation problem, but we're being asked to find y double prime. So the theory is the same. To find y double prime, I first have to find y prime. So by the way, for this particular problem, we could solve for y, but you'd get two answers, right? Because it says y squared. When you take the root, you're going to have a positive root and an even root. So in theory, we could solve this equation for y, but it would be a lot more tedious. It'd be a lot more work because we'd end up with two root functions, and then we'd have to take the derivatives of those. So here, I'm going to just do implicit differentiation. It's much more straightforward. I don't have to worry about solving for y first. I'm just going to start with the original equation, take the derivative of both sides with respect to x. So now let's make sure we get this. For 2x cubed, the derivative of x cubed is 3x squared, which I'm multiplying by the 2 that's already there. You get 6x squared. For 3y squared, remember y is a function of x. So that's a function of x squared. So I need to do the derivative of the outside. So here, this is going to be 3 times, the derivative of the outside will be 2 times y raised to the first power, times the derivative of the inside, which is just dy dx. So here you multiply the 3 and the 2, you get 6y dy dx, or 6y y prime. And obviously the derivative of 7 on the other side is just 0. So now you can solve for y prime here. I'm going to move the negative 6y y prime over and divide both sides by 6y. The 6's will cancel. I get y prime equals x squared over y. And now remember, we're trying to find the second derivative. So we're not done here. Don't forget here. We're trying to get to y double prime. So now I'm just going to take the derivative of both sides with respect to x. Now here, very careful. When you see x squared over y, what I want you to see in your head is this is x squared over f of x. And so if I'm taking a derivative of x squared over f of x, this is a quotient of functions of x, so we need to use a quotient rule. We need a quotient. So now I'm going to do my quotient rule. Square the denominator, and then in the numerator here, I'm taking the derivative of x squared, the derivative of x squared, which is 2x, times our original denominator, which is y. Minus, I copy down the x squared, and the derivative of y with respect to x is dy dx or y prime, you know, however you want to write it. And so now one final step I can do here is in the previous step, we solve for y prime. So I can plug in, I can replace y prime with x squared over y, and now we're just doing algebra. You know, when we finished that quotient rule, that was done. That was our last bit of calculus here. The rest of this is just algebra now. Replace the x squared, the y prime with x squared over y right here. And now just algebraic simplification. What you should notice is that, look, I've got a fraction in the numerator of my fraction, and we don't like that. So what I'm going to do is I'm going to get rid of this denominator here. That's this y term that's in right here. This y term that's in the denominator of the numerator. I'm going to multiply top and bottom by y, so it'll cancel that out. So when you multiply top and bottom by y, remember the y has to distribute. Y gets multiplied to this term here, so this y cancels, but y also gets multiplied over here. So this becomes a y squared, so I get 2xy squared minus x squared times x squared, all over. In the denominator, y squared is also multiplied by a y, so this will be a y cubed. So I end up with 2x y squared minus x to the fourth over y cubed. That's our second derivative. So I'm going to stop right here. The next problem involves finding the derivative with respect to y instead of x. So I think this is a good place to stop.